Nuclear chemistry continued, nuclear equations full set. So in this module, we're going to go over typical equations you might find on an exam, and these will include alpha, beta, and gamma decays, as well as examples of fission and fusion. And here you are asked to identify the missing particle and to identify the nuclear reaction type. Now, if you have the slide set printed out, you'll notice that there is one slide that looks exactly like this with no answers on it that you can use to practice on your own, and you can stop the video here and try them for yourself. There is a second slide that has all the answers, and we're going to go through these now. So let's look at the first example. You have uranium-234, and you would always name it by the name of the element and its mass number. Mass number is the same thing as isotope number. Remember that. So it's uranium-234, undergoes some nuclear reaction to become xenon-134, an unknown particle, and 3 neutrons. These are 3 separate neutron particles. Now, the first thing you need to do whenever you get these equations is to identify the mass number and atomic number for all the particles that are given to you. And you're trying to determine the mass number and atomic number for the missing particle, but we don't know the numbers for the neutron just yet. We need to fill these in. Well, you can always memorize the atomic number and the mass number for particles like neutrons and protons, or you can just think of them logically, and I would much rather you did it that way so that you don't have more to memorize. Now remember, what is an atomic number? Well, the atomic number is merely the number of protons that a particle contains. Well, a neutron contains no protons, so its atomic number is 0. And mass number is defined as the number of protons, which is 0, and the number of neutrons, which is 1. So our mass number is 1. So every neutron will have a 1 and a 0. And if you realize that, you can fill these in for all the other neutrons that might appear in your problems. So now that we have all the numbers filled in except for our missing value, our missing isotope or particle, now we do the calculating. And the simple rule is this: the total of the mass numbers on the left side of the arrow must equal the total of the mass numbers on the right side of the arrow. That's the top numbers. And the total of the bottom numbers, the atomic numbers on the left side of the arrow, must equal the total of the bottom numbers, the atomic numbers on the right side of the arrow. So 234 is the sum of all the mass numbers on the left, so 234 must be the sum of all the mass numbers on the right. Well, 234 minus the 134 is 100, but we also have 3 separate neutrons, and each one has a mass number of 1. So that's 3 more mass numbers we need to account for. So 100 minus the 3 leaves us with a mass number of 97. That's our top number. We do the same thing for the bottom number, the atomic number. 92 is our total. We have a sum of 54, an unknown, and 3 zeros, which is easy to deal with. So 92 minus 54 is 38. So we now know our particle, our isotope, has a mass number of 97, an atomic number of 38. We go to our periodic table, and you can only find atomic numbers on the periodic table. Never will find mass numbers on periodic tables. We look up 38, and we find that 38 is strontium. And now we can fill in our answer. It's strontium-97. And we can always do the check, make sure 234 equals 134 plus 97 plus 3 times 1. And that's true. And on the bottom, 92 equals 54 plus 38 plus 3 zeros. So we know we've got the right reaction. And now it's a matter of determining what the reaction type is. Well, we're starting with a very large nucleus, and we're breaking it up into 2 smaller nucleuses, nuclei, as well as 3 neutrons. And we don't really worry about the neutrons in this case, but we see that we definitely have split a big nucleus into 2 smaller nuclei, and we know that that is a form of fission. Looking at the second problem, we've got deuterium, or hydrogen 2, plus some unknown particle, produces a beryllium 7 and a neutron and a certain amount of energy. And when you see the energies, don't worry about them. They don't affect your calculation of what particle it is, and they don't affect what the reaction type is. They're just there to tell you this reaction is producing energy. But the fact is, every one of these reactions produces energy. It's just in some cases you will see the number provided. In this case, it's 3.38 mega electron volts, or million electron volts of energy. So we fill in our neutron, which we already know is 1 and 0. And now it's a matter of determining the two values for our missing particle. We know that 2 plus something equals 7 plus 1. Well, 7 plus 1 is 9. 7 plus 1 is 8. So 2 plus 6 must be our remaining number. That's our top number, our mass number. And on the bottom, we know 1 plus our unknown must equal 4 plus 0. Well, then our missing number must be 3. So we have 6 on the top, 3 on the bottom. We go to our periodic table, and we know that element 3 is lithium. So now we can fill in our actual formula here with lithium 6. And what have we done in this reaction? Well, we've taken two smaller nuclei, hydrogen 2, otherwise known as deuterium, and lithium 6, and made a bigger particle, beryllium 7. And yes, it has released a neutron in the process, but this would be a fusion reaction. We are fusing two smaller nuclei to make one bigger nuclei. It's always better to disregard the neutrons or protons that might be formed when you're determining which reaction type it is. Let's look at the third one. We have an unknown that's undergoing, obviously, an alpha decay, because you can see I've written the alpha particle here. But you have to remember, what is an alpha particle? An alpha particle is a helium nucleus that has a mass of 4, and helium has 2 protons. So now it's a matter of just comparing the sides. We have 214 plus 4 on the left, on the right side, so we must have 218 on the left side. We have 87 plus 2 on the right, so we must have 89 on the left. We look up 89. 89 is actinium. And now it's just a matter of filling it in. It's actinium 218. We don't need to say the 89. 89 means actinium. And this is an alpha decay. And you can write the alpha particle as just simply alpha. You could write it with alpha, showing that you know it has a mass number of 2 and an atomic number of, a mass number of 4 and an atomic number 2, or showing that you know it's helium 4. Any of those would be acceptable. And this is obviously an alpha decay. Let's look at the fourth example. You have krypton 92, which is becoming rubidium 92, and some unknown particle. So already you should see the mass numbers don't change. So the mass number of the missing particle must be 0. 0 plus 92 equals 92. But if you look at the atomic numbers, you've got 36 and 37. Well, what do you add to 37 to make it 36? Well, what you add is a -1. And that seems odd unless you remember about the beta particles. Beta particles have an accounted number for its atomic number of -1. It doesn't have a negative proton, but the reason why it's written as -1 is to show the fact that a beta particle is released whenever you are converting a neutron, in the krypton in this case, to a proton in the rubidium. So the atomic number goes up by 1, and to balance out the numbers, we write the beta particle with a -1. So we now know that our product is a beta particle, and you can write it as simply beta. That would have been acceptable. You can write it beta 0, -1, or you can write it where you identify the beta particle is in fact identical to an electron. It's just not the same origin. It's not the electron that's from the electron cloud. This is an electron that was formed because a neutron broke apart into a proton which stayed behind, and the electron, which is the beta particle, which is released from the nucleus. And this is obviously a beta reaction. Let's look at the next example. We have an unknown which is undergoing some nuclear reaction to become tellurium-137 and zirconium-97 plus 2 neutrons. Always fill in the identity for the missing particles that you know. Neutron is atomic number of 0, mass number of 1. So we know that our mass number of our unknown must be 137 plus 97 plus 2 times 1. Don't forget to multiply the 2. And when you add those numbers up, 137 plus 97 plus 2, you will get 236. And if you're not quick with the math, absolutely use the calculator on this. In any case, I would use it, even if you're good at math, I would use the calculator to make sure you don't make mistakes on problem sets or labs or exams. We do the same thing for the bottom. We have 52 plus 40 plus 2 times 0. Well, obviously 2 times 0 is just 0. So 52 plus 40 will give us 92. Well, 92 is our atomic number. We look up on the periodic table and we find that 92 corresponds to uranium. And what have we done in this reaction? Well, we've taken uranium-236 and split it into 2 smaller nuclei, tellurium-137 and zirconium-97, plus the 2 neutrons, which we're not going to worry about. But this would be an example of a fission reaction. Again, you're starting with a large nucleus and producing 2 smaller nuclei. Let's look at the next example. We have lanthanum-132M, and that should be your tip-off right there. The second you see a number with an M or an M1 or an M2 or just a star, that tells you it's what we call a meta form. They're not quite isotopes. These are isomers of the nucleus. So it's a different form of the exact same nucleus. In other words, the nucleus of 132M lanthanum is exactly the same number, has exactly the same number of protons and neutrons as just plain lanthanum-132. They're just organized in a different shape in that nucleus. And you can see this is a gamma decay because I've written the gamma particle. And it's always good to remember that a gamma has no atomic mass. It has no mass at all. And it has no atomic number. There are no protons, and it's not involved in converting protons to neutrons or neutrons to protons. So it's 0 and 0. And that makes the math extremely easy. So the new particle also has a mass of 132, also has an atomic number of, a mass number of 132, or isotope number of 132, and an atomic number of 57, so it's still lanthanum. And this would be a gamma decay, a very typical gamma decay, where you're just converting a high-energy form of an isotope to a low-energy form of an isotope, and that energy goes somewhere in the form of a gamma particle, a photon of light, of high-energy light that's released. Next example, iodine-108. And this produces an element whose symbol is Sb, and actually there are 3 different pronunciations for the element whose symbol is Sb. The American English typically pronounces it as antimony. The British English usually pronounces it as antimony, and then I've heard antimony as well. So any one of those is acceptable. If you say any one of those, that's fine. The Sb is because the ancient Roman name for this was stibium, which might be a little easier to say, but it's antimony if you're in America. That's the typical pronunciation, but any one of those is perfectly acceptable. But you also have this unknown product, and you can see that 108 is becoming 104 plus something. Well, 104 plus 4 would be 108, and 51 plus 2 would be 53. Well, we know that element number 2 is helium, So this is a helium-4 nucleus, and we can see that it's being, well, we can see that it's being split off from a larger nucleus, and we can write it as helium-4, or we can identify it as, in fact, an alpha particle. And you can write just simply alpha, or you can write alpha with the 4 and the 2, or helium with the 4 and the 2. Any of those would be acceptable. This is an alpha decay. The next example, aluminum-28 is undergoing some reaction to become some new particle plus a beta particle. And beta is the one that students have the most trouble remembering. I would just remember beta particle release does not change the mass, and just put a -1 for a beta particle. It will save you a lot of heartache if you just remember beta is 0 and -1, and alpha is 4 and 2. These two particles I would memorize just to make your life easier when you're doing these calculations. So now it's a matter of figuring out the missing numbers. 28 equals something plus 0. Well, obviously that's 28. And 13 equals something -1. Well, that would be 14. And if we look up 14 on the periodic table, we see that's silicon, and we can write that as silicon-28. Now, I don't usually do it this way. I just remember that when you have a beta decay, the product will have the same mass and go up 1 atomic number. This is very unusual. You're losing a particle, but the atomic number goes up. And you just have to remember that. But if you want to do all these math problems where the beta might be the missing particle, or the beta is the known particle in your equation, or you don't know the starting one, the starting isotope, or you don't know the final isotope, it's really best to just remember beta is 0 and -1, and this will definitely make doing these equations easier. And obviously this is a beta decay. And then the last example, the second to last example is helium-3 plus hydrogen-3. Hydrogen-3 is also known as tritium. Produces a new particle plus an extra proton and an extra neutron and a lot of energy. Well, let's figure out what the missing particle is. First, we need to fill in the numbers for a proton and a neutron. Well, we know a neutron has a mass of 1, but no protons, and a proton has a mass of 1 and 1 proton. So now we have all our numbers except for our missing value, and now it's a matter of looking at the top numbers, the mass numbers. We have 6 on the left, we have to have 6 on the right. Well, we have 2 here, so the missing number is 4. And if we look on the bottom numbers, or atomic numbers, we have 3 on the left side. We've accounted for 1 of them with the proton, so the remaining 2 must be in the new particle. And that is, in fact, another helium-4. But this helium-4 is not an alpha particle. Why is it not an alpha particle? It did not get released from another nucleus. This alpha particle was the result of fusing together 2 smaller nuclei to make 1 bigger nucleus. And therefore, this is a fusion reaction. So please do not confuse a fusion reaction that happens to produce helium-4. They can produce a lot of other things besides helium-4. You've already seen one example up above in the second problem here, where the product is beryllium-7. That's a fusion product. But when helium-4 is formed in a fusion, this is not an alpha decay. This is a fusion product. And then the last example is a little hard to see here. We've got Einsteinium-255. Einsteinium, named for Albert Einstein. In this case, it undergoes a reaction to produce tin, that's SN, tin, 128, plus some unknown isotope. Well, 255 minus 128 is 127, so that's the missing mass number. And 99 minus 50 for the tin leaves us 49. I'll write it right there, 49. I'll stick it a little above. And then we look up 49. 49 is indium. Indium is named for the Indus River in India and I believe in Pakistan. So that is our answer, and we fill that in, indium-127. And because we're taking a large isotope or a larger isotope like Einsteinium-255 and splitting it into two smaller nuclei, tin-128 and indium-127, this is another example of a fission reaction. And that is it for this unit.